You'd be famous.
You could rack it up like diamond play button.
All right, so let's look at this. So we'll see how you guys did. Part A says, calculate the total mechanical energy. So this one's worth 2 points. It says for an indication of the total mechanical energy, sum of the kinetic and potential energies. If you have E is equal to U plus K, boom, dudes, nailed it, right? And then for the correct calculation of the numerical value of the total energy, E is equal to 7 joules. I do not know to what extent they like, if you don't put the right unit, they mark you down. I don't know, okay? So I would err on the side of always put the unit. I think it's just an easier way to go. Yeah?
What if I put just E equals U plus K and left the X out?
Nope, that's fine.
Okay, that's fine. It's common choice, so,
What they're indicating here is that the potential energy is a function of the position.
Yeah.
And the kinetic energy is actually a function of the position also. But U plus K is fine. Okay? Hello? 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 Okay? B? B's a three-pointer. It says, calculate the x-coordinate of any points at which the object has 0 kinetic energy. Let's see what they said. So, 3 points. It says, for an indication that E is equal to U when K is equal to 0. Does that make sense? Yeah.
So if I wrote U is equal to 7 joules for my previous problem.
I think that, well, so it says here, for substituting E from the previous problem. Does that make sense?
So in the equation.
So you're always going to start from some general principles. Even if you started with something like E is equal to U plus K, K is equal to 0, therefore, I'm going to substitute the 7 in from the previous part. Now, so you get, for substituting E from part A, good job. This also means if you jack this up, but you substitute in your correct value, your value for this one, you might still get it. Does that make sense? And then for indicating plus and minus signs in the final numerical answer. I heard Claire say that. She says, don't forget the plus and minus. If you got to take the square root.
Thanks, man.
Is that cool? Oh, whoa.
Oh.
Don, what are you doing? Settle down. Okay. 3 says, calculate the magnitude of the momentum of the object at 6. Okay? So for clear indication that the kinetic energy is the total energy minus the potential. So you really want to indicate the fact that you are somehow going to calculate the total, or calculate the kinetic energy by taking the total energy and subtracting off that. Okay? For using calculated K to solve for V, that's another point. And then for substituting the calculated value of V in an expression for momentum, boom. Yeah.
If I wrote like, so if I said, so 7 equals K plus U, is that wrong?
Nope, that's good.
Oh, okay.
That's perfect.
So that's 1 point, and then it's 3 points, right, total?
Yep, 3 total.
So then what's the second point for?
For calculating K to solve for V.
So just
So,
plug them in, what happened, E squared?
yep. So you got V is equal to 1.92 meters per second, and then getting a value for momentum. So the point is for like this section here, where you say, okay, I'm going to use K to solve for V. I know the K value, let me plug it in, here's my V value. So you need like these 3 steps here. Okay? I don't know what this is. You know what this is?
What's that say?
It says P is equal to 2mk, square root of 2mk. Is that like the root mean square law?
No idea.
I don't know either.
I ain't got no clue.
D says, calculate the magnitude of the acceleration of the object as it passes through 0.6 meters. So this actually, I find this one a little bit challenging, because what are you trying to find out? The acceleration. What do you need to know the acceleration? You need 2 things.
Force and mass.
Force and mass, right? But you don't have the force. How are you going to get the force?
Derivative.
You're going to use the derivative function, right? So this is one of our basic principles. Okay? So, for a correct relation between force and potential energy, so if you write the force as the negative derivative of the potential energy function with respect to the position, that's a point. Cool? Oh, it's like it says, the point was awarded if the negative sign was not included. Oh, that's nice. For an expression, So you're going to calculate it. So if you can get negative 8x, great job for you. Divide by mass. Good work. And there you go. Bob's your uncle.
This was 2 points too.
Yeah. What?
Did they show the acceleration being positive?
So it asks for the magnitude of the acceleration.
Oh, okay.
So if we have negative, that'd be wrong.
You're good too.
Yeah.
What's the other way you could do this problem?
I have no idea.
E equals U plus K.
This is cool. So you're going to use this for a correct energy relationship. So total energy is equal to U plus K. You have 4x squared plus 1/2 mv squared. But you're going to notice that this is x squared and this is v squared. But x and v are related, aren't they? So you can rewrite this as, so we have 14,
It seems like they just multiplied by 2 on that step.
so they did to get rid of the half. And then it says, for taking the derivative with respect to time for each side of the equation. So over here you take dx dt, and over here you do dv dt. Super annoying. I would not do that.
That just seems like a great way to get
Oh, and
the
dx
problem.
over dt is velocity.
That's right.
That's confusing.
I know.
Nope.
I would not do that. We'll talk about these. We'll talk about these other points
Luke
another time.
Babcock, do you understand this?
All right. More clear or less clear? How'd you guys do?
Good.
Good. What I want to do is I would like to practice these, try to figure them out as a small group, and then analyze the rubrics, because I think there's a lot to be had for saying, like, how was this scored there? So that you can kind of craft the way that you want to start to respond to them to go with what they're looking for. Does that sound good?
Yes.
Okay. Did I give you tonight's? Yeah, it's blocks on a ramp.
Yeah.
Yep.
Okay.
Are we gonna ignore the graphs in the back?
We'll come back to them.
Those were confusing.
Well, there's a specific piece of information you need, so don't worry too much about it. All right, I'm going to do some drawings. I would like you to draw along with me. Mr. Off and out of sight, you are neither off nor out of sight.
Sorry, my phone is literally broken right now, I can't even use it.
Okay, you don't need it right now.
Could you
You
just
don't need it
No,
right
I'm
now.
trying to troubleshoot the problem.
slide it right into your bag, man. You're good to go.
Oh, hold on, I think it fixed itself. Never mind. I'm gonna shut it off.
What a great idea. Okay.
We have a sub. She's gonna
Oh,
love
shut
us.
off like that.
All
Can I
right.
get a shout out?
So, I have an interesting thing over here. This is a very smooth. This is a very smooth pulley. Okay. Now it's got the string, and I've wound the string around here. Okay. You see how I wound the string around here?
Yeah. Are you gonna hold it?
I'm not gonna. I'm gonna put a little.
I think you gotta show that the difference.
I'll put a little dude on here.
Supposed to be writing this or not?
What's gonna happen? Not yet.
It's gonna accelerate angularly.
No. Oh.
Okay. Now, as you watch this, a couple things happen. What's one thing you saw happen?
The wheel sped up?
As the wheel spun, did it speed up its rate of spinning?
Yes.
It did. If you watch it, just watch right up here.
You can even see it in the weight too.
Does it look like it's getting faster?
Yeah.
It does, right? But what else did you notice happened? What happened to the weight?
It went straight down.
It went straight down. Same speed the whole time?
No. Oh.
I don't know.
It sped up, but just downwards, it wasn't spinning or anything.
Let's watch.
Oh.
Did it speed up the whole time?
No.
Yeah, I did. Okay.
Yeah. It might not actually be super easy to see. Well, I'll put it here and we'll see. It might be a little easier to see. Okay. I mean, obviously it has to speed up a little bit because I'm releasing it from rest.
Yeah. Yeah, it's
Yeah, it's-
Speeds up the whole time, right?
Yeah.
So what we're gonna do is we're gonna try to draw a diagram for this to see if we can't relate the things that are happening. Does that sound good? Okay. So, draw along with me, por favor. So here is the pulley. Is that cool? All right. Now, the pulley itself has some weight, doesn't it? That's the big mg for the pulley. Is that all right? Now,
But the stand is like, it's got a.
yes, the stand is actually supporting it upward. To the extent that those two forces are equal, they're not exactly equal, but we'll talk about it in a second.
How does that work? Because it's not a,
So that's the force of the support, keeping the pulley upward. It's a little bit bigger. I mean, you can actually, if you just look here, you can kind of conceptualize the fact that it should be bigger because on the support, the weight of the pulley and also the weight of the hanging thing. Do you see how, does that make sense? So it's a little bit bigger, it's a little bit bigger than that.
would the pulley be considered the whole, like, even the thing that connects to the support?
Yeah, so we're just talking about the pulley and then the support. It's connected through the middle, so it's okay. Now, when you watch this, okay, does the pulley speed up in its rotation? It
Yeah.
does, right? So what's causing it to speed up?
The force of the weight of the string on the outside.
So I love where you guys are at on this. You are 100% correct. We think initially it should be the weight, but is the weight touching the pulley?
No.
No, what's touching the pulley?
The string.
The string, right? So I'm going to do it on this side. So it's on my left, your right, is that correct?
Yep.
All right, so there it goes. Okay. So when I do that, this is,
Feels like constant.
what do we call a force by a string?
Tension.
Tension. Mid-yawn.
Now, let me ask you this, and this is important. Is the pulley as a whole object accelerating up or down or left or right?
No,
No. What does that tell you about the forces?
they should be equal.
So I think the force is balanced. So the linear acceleration is equal to 0. Therefore, the net force in all directions is equal to 0. Does that make sense? So what does that tell you about the force from the support then?
Wow, wait, how's
It's mg plus force tension.
Yes.
how's the acceleration 0? I thought you said it was speeding up, so when it.
The little object is speeding up,
But it's not.
but the pulley,
Oh,
It's staying still.
the pulley is not accelerating up or down, true?
Oh, we're talking about linearly.
So the force from the support is a combination of the weight down and the tension down, because those are both in down direction. Is that all right? Guys feel okay about that? So this is one of our frameworks for this. Does that sound good? All right. What about the little hanging object? Okay. What about our little hanging object? Oh, I drew it on the wrong side. Even though I said I was going to put it on
The right side.
my left, your right, I drew it on the wrong side anyway. What a moron. Who's in charge of this?
Sod.
Simon.
Okay.
Okay. This is the scenario, true? So if I want to do a force diagram for the little hanging object over here, what are the forces on this guy?
The string and the earth.
All right, Earth is pulling him down, we'll call that little mg. What's the string doing? Strings pulling them up. More or less than the earth force. How do you know it's less?
Accelerating down.
Yeah, because it's accelerating down, right? So are the forces balanced on this guy?
No.
No, not at all. So can we write a net force statement for this guy? Well, we know F net's equal to MA. Okay. F net's equal to MA. How am I going to represent mathematically the net force on the hanging guy?
Just MA minus FP.
I agree. So I think that that's the way to do it to keep the value positive. That way you really don't have to keep track of the signs in that way.
And this is still all linear, like this is an
Yep.
angular, right?
Right, we're all still linear. We're about to jump into the angular waters here in a second.
That's-
So the little mass times his acceleration is equal to mg minus ft.